Alright, this is the first problem of AP Physics 1 2024 free response questions. Here's the question. So let me read the problem statement quickly at the beginning. A block of mass m is released from rest at point A, a height 6r above the horizontal. After being released, the block slides down a track as shown. When released from point A, the block does not lose contact with the track at any point. Points B and C are located at the highest points of their respective circular loops, both of radius r. All frictional forces are negligible. So, before we start here, let's highlight the important points in the problem statement. The first being, the block started from rest, so initially it has got zero speed. After released, where is it? Here it is. The block does not lose contact at any point. So all the time we have got normal force, the force exerted by the surface to the block. Whatever is the direction, we have got non-zero normal force. And all frictional forces are negligible. So we have got conservation of mechanical energy in the entire voyage, let's say. All right, before we start again, one more thing is useful to do, which is, this is energy problem. So let's quickly analyze the energy situation at given points. Let's start with point A. At point A, we have got only potential energy because we are starting from rest, no speed, no kinetic energy. So the potential energy at point, gravitational potential energy at point A, which is mgh. In our situation, capital M, G, the height is at the beginning given as 6r. So we can bring 6 here. So 6 mgr. What about kinetic energy at point A? 0. At point B, the gravitational potential energy again, mg, height of B. The height of B, this is a circle with radius r, so the highest point has got height as 2r. So it's going to be mg 2r, so we can bring 2 here, 2 mgr. Because mechanical energy is conserved, at the beginning we have got potential energy plus kinetic energy equals 6 mgr. So at point B, again, mechanical and the sum of mechanical energies, potential energy plus kinetic energy, should be 6 mgr. Because potential energy is 2 mgr, kinetic energy must be 4 mgr at point B. Now, point C also, potential energy at point C is mg, height C. The height of C from the ground, 2r plus another 2r, 4r. So it's going to be 4 mgr. Thus, kinetic energy must be equal to 2 mgr, with the same logic as we discussed at point B. Okay, diagram A shows an energy bar chart that represents the gravitational potential energy UG of the block Earth system and kinetic energy K of the block at point A. We can see we have got some gravitational potential energy and 0 kinetic energy. At the beginning we have got kinetic energy equals to 0 at point A and potential energy equals to 6 mgr. Alright, here is a question. Draw shaded regions in diagram B that represents the gravitational potential energy UG and kinetic energy K of the block Earth system when the block is located at point B, a height 2r above the horizontal. Now, the analysis we have done before previously can help us to draw the diagram. Here we can see at point B we have got gravitational potential energy 2 mgr and kinetic energy equal 4 mgr. So relative heights will be accordingly. Gravitational potential energy 2 mgr, that's why it has got 2 units high, and the kinetic energy 4 mgr, which is 4 units high. Part B. Starting with conservation of energy, derive an expression for the speed of the block at point B. Express your answer in terms of R and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference book. So basically here the principle is the conservation of energy. Energy initial is equal to energy final. So initially we have got only gravitational potential energy at point A. No kinetic energy. We can write plus 0, or we can just leave it as potential energy only. Equals to gravitational potential energy at point B plus kinetic energy at point B. So quantity is coming, 6 mgr is equal to, at point B, 2 mgr plus kinetic energy equation half mv square. So we can send 2 mgr on the other side. It's going to be 4 mgr is equal to half m speed square. The mass can be cancelled. The 4.5 goes, instead we have got 8 here, so v is going to be square root of 8r. Next question. On the following dot that represents the block, draw and label the forces, not components, that are exerted on the block at the instant the block slides through point C. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So if we go back to the diagram again, we can see the point C. Now, you remember we highlighted the point where it says the block does not lose contact. This was important because we understood from that statement that always we have got normal force. So at point C, because the block is going to go up, it's kind of upside down situation, the normal force will be pointed downwards. So we have got normal force which is pointed downwards. Let's label it as Fn. And of course we have got the earth, the gravitation, also pointed downwards. The point is they should be parallel. The quantities are not clear here, so they can be longer or shorter than each other or equal. It totally depends on you, but both of them should be pointed downwards. A student claims that 4r is the minimum height of point A, such that the block can slide through point C without losing contact with the track after the block is released from rest. Briefly explain why this claim is incorrect. Good. Now let me try to draw one more time the situation. Something like this, right? So if you are going to release from 4r and the final point at point C, this point C, it's also 4r from the ground. Now we can see both of them are having the same height. Logically, at the beginning we have got potential energy, which is converted to kinetic energy in between, and when it comes to again the height of 4r, we will have only potential energy. There will be no kinetic energy, no speed. So if there is no speed, there will be no tracking, and it's upside down. There will be no normal force. It's going to fall down straight to the earth. So what do we write here? If released from 4r height, there will be no kinetic energy at point C. Since the highest point of C is also highest point of at C is also 4r. Since there is no speed at point C, it will not continue to loop. Lose contact with the track and fall down. All right, this is free response question number 2. Here's the problem statement. You can see the figure above and we can understand that this is an experimental problem. So let me read the problem statement quickly. A student hangs a spring of unknown spring constant K vertically by attaching one end to a stand as shown in figure 1. The other end of the spring has a small loop from which small cylinders can be hung. In addition to the spring, the student has access only to a variety of cylinders of unknown masses, a stopwatch, and a digital scale. Alright, so these are the tools available. We have got cylinder of unknown masses, and we have a stopwatch and digital scale. Alright, part A. Design an experimental procedure the student could use to determine the spring constant K of the spring. In the following table, list the quantities that would be measured using only the provided equipment in your experiment. Define a symbol to represent each quantity. In the space below the table, describe the overall procedure. Provide enough details so that another student could replicate the experiment. Let's go to the table. All right, here is the table. Now, we have this spring and we have got different masses. So to measure the K, we can use the oscillation of spring mass spring system, where the period is equal to, you can check it from your formula sheet, it's going to be 2 pi square root of m over k. Now, we can use this relationship. Here, what are the variables? So here we have got period changing, and we can also change mass. How we are going to do it? A mass can be hung, little bit pulled, then released, and it's going to oscillate. And the oscillation, if we ignore the friction, it's going to be periodic. Which quantities need to be measured? First of all, time. Second, mass. So symbol for quantity of time, let's say period with capital T and mass with M. Stopwatch measures the time and the digital scale measures the mass. Now, procedures. First of all, let's start with setup. To set up, we can say take an unknown mass cylinder, measure its mass with scale, hang it on the spring. Okay, the setup part is done. Now, second part, there must be action. The action here is pull the cylinder a little bit and release. But at the same time, start the stopwatch. Simultaneously start the stopwatch. Here, it is very hard to measure one oscillation. The trick here is, probably you did it in the physics labs, you count 5, 10 oscillations. I prefer 10 because it's easy to divide by 10. And measure the time. Count 10 oscillations and measure or record the time taken. To increase accuracy, repeat it few times. Now, number 5, we have to change the independent variable here, which is the mass of the cylinder. Do the same or repeat, do the same procedures for several, at least 5 cylinders. Several different cylinders, let's say. So that each time the mass would be different. Okay. Next. Indicate the quantities that could be plotted to produce a linear graph whose slope can be used to determine the spring constant K of the spring. Let's remember the equation. So period is equal to 2 pi square root of L over G. We want to have a linear graph, so we have to linearize. So we have to get rid of the square. I always confuse simple pendulum with block spring system. Block spring system must be square root of m divided by k. So to get rid of square root, we just take square root of both sides. So t square 4 pi square m over k. So we can see one side we have got t square, let it stay in the y-axis. So equation resembles to y is equal to mx. So here the y is equal to t square, x is equal to m. I will continue. The slope, or let me write the slope here. The slope is going to be 4 pi square divided by k. Okay, on horizontal axis it should be m. Briefly describe how the slope of the graph would be analyzed to determine the spring constant k of the spring. So according to our quantities, the slope is going to be equal 4 pi square divided by k. So the k spring constant is going to be 4 pi square divided by slope. Next question. In a different experiment, we can see the setup is different in figure 2. In a different experiment, the student attaches one end of a spring to a force sensor that is attached to a wall. So this side we have a wall which is not moving. The other end of the spring is attached to a card with mass 0.25 kilogram. The student places a motion detector to the right of the card as shown in figure 2 and pulls the card to the right a small distance so that the spring is stretched. The student releases the card from rest and the card spring system oscillates, obviously. The following graph shows the velocity of the card and the force exerted on the card by the spring as functions of time. So first of all, we can see velocity versus time graph and force versus time graph. All right, let's go to question and we can answer them using the graphs given. First question, part C, first question. Using the data in the velocity time graph, calculate the change in kinetic energy of the card from time is equal to 0.5 second to time is equal to 2 seconds. So we want to find change in kinetic energy. Kinetic energy time is 2 seconds minus kinetic energy time is 0.5 seconds. And we know that kinetic energy is equal to half mv squared. So in this case, it's going to be v at 2 seconds square minus v at 0.5 seconds square. So half, the mass is 0.25. Let's look at the speeds now. Now at 2 seconds, we can see the speed is, velocity at 2 seconds is equal to 0 and velocity at 0.5 second is 0.3 approximately meter per second. In that case, it's going to be 0 minus 0.3 square, negative 0.011. The unit of kinetic energy is joule. Second, using the data in the force time graph, estimate the change in momentum of the card from time is equal to half second to time is equal to 2.5 seconds. Briefly explain how you arrived at your estimation. So, change in momentum, dp, is equal to the area under the graph. If you look at it from 0.5, which is here, to 2.5, which is here. Now the area, we are talking about this and that. Now we can see at the beginning we have got negative area because the line is below the zero, and towards the other second half we have got approximately equal area, but positive because it is above the zero line. They both cancel each other and total area is zero. Thus, change in momentum is zero. Third, do the data from the velocity time graph confirm your estimation from part C? Second, briefly explain. Let's check again. So here it is 0.3 meter per second, and at 2.5 it's again 0.3 meter per second. They are confirming each other. The reason, at both times we have got same velocities. Yes, the velocity time graph shows that velocities are same at both time is equal to 0.5 second and time is equal to 2.5 seconds. Since change in momentum delta P is equal to final momentum minus initial momentum, which is m final minus initial, it is equal to 0 for velocity final equal to velocity initial. Free response question number 3. From the figure we can see that it is a rotational dynamic question. Here is the problem statement. The left end of a uniform beam of mass m and length L is attached to a wall by a hinge, as shown in figure 1. One end of the string with negligible mass is attached to the right end of the beam. The other end of the string is attached to the wall above the hinge at point 1. The beam remains horizontal. The hinge exerts a force on the beam of magnitude Fh, and the angle between the beam and the string is theta 1. Part A. The following rectangle represents the beam in figure 1. On the rectangle, draw and label the forces, not components, exerted on the beam. So first let's analyze the figure. Here we have the beam. Obviously on the string we have got tension force, gravitational force from the center of mass pulling down, and we have got hinge. There is horizontal and vertical components acting on it, so in total the force will be directed in this way. So on this figure we will one more time show these forces. Gravitational force from the center to the down, tension force along the string, and the force exerted by the hinge as shown here. Next, the string is then attached lower on the wall at point 2, so we are changing the attachment point of the string on the wall, and the beam remains horizontal as shown in the figure. The angle between the beam and the string is theta 2 this time. The dashed line represents the string shown in the figure 1. Alright, the magnitude of the tension in the string shown in figure 1 is Ft1. The magnitude of the tension in the string shown in the figure 2 is Ft2. Indicate which of the following correctly compares Ft2 with Ft1. So what do we know already? We know that angle 1 was bigger than angle 2. Now, here we can use torque to analyze and compare the quantities. So torque clockwise and torque counterclockwise. In both situations, must be balancing each other because the beam is not moving. Okay, what's causing clockwise torque? Gravitation is causing clockwise torque, and the string force is causing counterclockwise. In both cases, the horizontal component of the string, this is Ft2, right? So it's going to be Ft2. So in both cases, vertical component of Ft must be same to balance the torque created by the gravity. But in the second case, we have got smaller angle. That means the tension force must be bigger to produce same vertical force. So first of all, we determined that the tension in the second situation is bigger. How we explain? Let's start with the torque. Torque from Fg, from gravity, is balanced with torque from the tension in both cases. Therefore, vertical components of both Ft1 and Ft2 are equal. Now, Ft2 must be greater in magnitude to have same vertical component at smaller angle, at theta 1 bigger than theta 2. Theta 2 is smaller than theta 1. Next question. Starting with Newton's second law in rotational form, derive an expression for the magnitude of the tension in the string. Express your answers in terms of m, theta, and physical constants. All right. The Newton's second law, net torque, or we can write in this form, net torque is equal to inertia times angular acceleration. Now, what's angular acceleration in the situation? Nothing is moving, nothing is accelerating, so 0. Torque net, clockwise, counterclockwise. Let's label counterclockwise. Traditionally, we take positive, clockwise, we take negative. So counterclockwise, it's coming from gravity. So gravitation force Fg, which is equal to mg, and the distance from the hinge is L over 2. So it's going to be mg L over 2 minus Ft times sine theta is the force. The distance is this times length. So it's going to be Ft sine theta times L is equal to 0. So tension force must be mg divided by 2 times sine theta. Part D. Is your derived equation in part C consistent with your justification in part B? Explain your reasoning. So here in the part C, we see that tension force is inversely proportional to sine theta. In part C, we see that Ft is inversely proportional to sine theta. So, for smaller angle, Ft becomes bigger. Therefore, it is consistent. Next question, part E. The string is cut and the beam begins to rotate around the hinge with negligible friction. On the following axis, sketch the angular speed of the beam as a function of time for the time interval while the beam falls out before the beam becomes vertical. So, at the beginning, we have this situation. We have got gravitation force. Now, tension is gone. What is going to happen? There is only one torque. Clockwise, it is going to rotate. And we have got maximum angular acceleration because we have got maximum torque at the beginning. When it becomes completely vertical, there is no any more force which is rotating it minimum or 0. But of course, meanwhile, we will have some angular speed, and it will, if there is no friction, it will hit the wall. Otherwise, it will just continue in rotation to the other side. So what do we have? At the beginning, we have got 0 angular speed. It is increasing at higher rate because at the beginning we have got maximum angular acceleration, but this acceleration is slowing, so we will have until it becomes horizontal. At peak point, when the beam is vertical, there is no angular acceleration, and the angular speed will be maximum. Alright, this is response question number 4. Here's the problem statement. From the figure we can see it is about simple pendulum. Problem statement. A simple pendulum consists of a small sphere that hangs from a string with negligible mass. The top end of the string is fixed. The sphere is pulled to point A so that the string makes a small angle theta with the vertical as shown. The sphere is then released from rest and swings through its lowest point B. The work done on the sphere by Earth between point A and B is WE. The pendulum is then taken to planet X. The mass of planet X is the same as the mass of Earth, but the radius of planet X is greater than the radius of Earth. The sphere is again brought to point A, displaces theta from the vertical, released from rest, and swings through its lowest point B. The work done on the sphere by planet X between point A and B is Wx. Justify why Wx is less than We. So here, let's quickly analyze. We have got point A, which is, let's say, at height of h from the equilibrium. H is vertical height of point A from point B. So here the work done is change in potential energy, which is mgh, right? In both cases, we are going to have same h, but because the planets are different, the g, gravitational strength, might be different. How it's different? The gravitational strength is gm over r square. So for Earth, it is g mass of Earth over r Earth square. For the planet X, it's going to be g mass of X divided by r x square. The masses are same, let's say m, but the planet X has got bigger radius, which means that it has got smaller gravitational strength. If on Earth it is 9.8, on planet X it is smaller, maybe 9, maybe 8. So, because g is small, the work done must be less. Let's bring everything together. Let's start with the work concept. The work done on the sphere depends on gravitational strength and the vertical displacement on g and vertical displacement. Let's call it h. Let me write also equation. Due to work is change in potential energy is equal to mgh. Now let's compare, let's justify why planet X has got lower g. Since the planet X has greater radius and same mass. That's critical because if mass was different, the situation could be different. It has smaller g. Again, let's write the equation due to g is being equal to constant times m over r square. The h is same in both cases. Therefore, Wx was less than We. All right. Next question. A new pendulum is made by hanging the same small sphere from a different string with negligible mass. The new string is slightly elastic, and the length of the string may increase or decrease depending on the tension applied to the string. On Earth, when the sphere is displaced theta from the vertical and released from rest, the new pendulum oscillates with period Te. The new pendulum is then taken to different planet Y. The radius of planet Y is the same as the radius of Earth, but the mass of planet Y is larger than the mass of Earth. On planet Y, when the sphere is again displaced from the vertical and released from rest, the new pendulum oscillates with period Ty. In a clear, coherent paragraph length response that may also contain drawings, explain how Ty could be larger than Te, but also could be smaller than Te. Alright, we are dealing with both scenarios now. It could be bigger and smaller. So what's happening? Let's start by drawing. Let's say this is happening on Earth. So we are having, this is Earth, let's say E. We are having this situation. So we are having length L. We are having pendulum here. Now we are having gravitational strength of G, which is directed down, and we are having period T Earth. But on another planet, planet Y, what do we have? The L. At Earth it was L, it was elastic. Because it was elastic, we are not sure if it's going to be same or not. Let's say Ly. Similarly, because the other planet has got different mass, even if the same radius, it has got different G, let's say Gy, and also the period of Ty. So start with the equation. So what's the equation? T is equal to, so we can see that is related to the square root of L, but inversely related to the square root of G. Let's start with the gravity. The planet Y has a greater gravitational strength. Why? Since it has got more mass and same radius. So more concentrated mass, it produces more forces, more gravitational strength. Since the period is inversely related to 1 over square root of G, so period is inversely related to the square root of G due to 2 pi L over G. Ty could be smaller on planet Y. Basically, stronger gravity makes it to swing forward and backward faster. Now, this was the first scenario. The second scenario, we also have another factor here, the length. Because of different gravitational force, the pulling is different. If you have stronger gravitational force, the pulling will be more and the length will be more. So in planet Y, the string will be elongated, stretched. Because of that reason, it's possible that the period increases for longer length. If the increase in the length is more than increase in the G, we are going to end up with longer period. So, second scenario, however, the period could be larger on planet Y too, because it is also proportional, because period is also proportional to the square root of L. On the planet Y, gravitational force Fg is stronger due to greater G. As a result, the elastic string can have if L increase more than G, the period on the planet Y could be longer. Alright, free response question number 5, the last problem. Alright, from the figure we can see it is about collision. So momentum and energy concepts are involved. Here is the problem statement. At time t is equal to 0, block A slides along a horizontal surface toward block B, which is initially at rest, as shown in figure 1. The masses of blocks A and B are 6 kg and 2 kg respectively as shown. The blocks collide elastically at time is equal to 1 second, and as a result, the magnitude of the change in kinetic energy of block B is 9 joules. All frictional forces are negligible. Part A. Determine the speed of block B immediately after the collision. So at the beginning, block A has got some initial speed, let's say block A initial speed, and the block B initially not moving. Now we can see that the change in kinetic energy of block B is 9 joules, which is converted in the form of speed. So at the end, the block B will have, finally block B will have 9 joule energy, which is equal to 100. So from there, let's also write what is the mass, 2 kg. From there, block B will have 2 cancels, so square root of 9, which is 3 meter per second. Next question. The graph shown in figure 2 represents the position x of block A, block B, and the center of mass of two block system as functions of time between time is equal to 0 to time is equal to 1 second. On the graph in the figure 2, draw and label 3 lines to represent the positions of block A, block B, and the center of mass of the two block system as functions of time between 1 to 2 seconds. Each line should be distinctly labeled. Alright, let's start with the center of mass. Because there was no friction, the speed of center of mass is not going to change. So it's going to continue with the same slope, because here the slope is representing the speed. We are going to have the line which is continue with the same slope as previously. So if you have a ruler, it is much better. Let's say I have a ruler too. It should have the same slope. Okay. Second, what else do we know? We already calculated the block B is going to have speed of 3 meters per second. So in 1 second, it's going to move 3 seconds. So it's going to be so it should go from 2 meters to 5 meters like this. All right. Now, finally, so let's quickly label this also. This is the center of mass. This is block B, and we have block A left. We have to calculate the speed of the block, the velocity of the block A after the collision, to be able to draw the line in this graph. So let's use the concept of conservation of momentum. Initial momentum is equal to final momentum. So initially, what do we have? We have got only block A moving. So it's going to be mass of block A times speed of A initially is equal to, finally we have got two blocks moving. Again, block A, speed of A finally, this is what we are trying to find, plus mass of block B times speed of B finally, which is 3 meters per second. Now substitute number 6 times initially we also from this graph can understand what is the initial speed of the block. It is the slope, so it's going to be what? 2 meters per second. It moved 2 meters in 1 second. So 6 times 2 is equal to 6 times velocity A final plus mass of B is 2 kilogram times 3. So velocity A final is going to be 1 meter per second. So in 1 second, the speed is going to increase by just 1 meter. Sorry, the position is going to change by 1 meter. So the graph line will look. Let's label this as block A. Next question. Consider if in the original scenario, instead of colliding elastically, the blocks collided and stuck together. Inelastic collision. Describe how the line drawn for the center of mass in part B would change, if at all. Briefly justify your response. Now we shifted to inelastic collision. Energy is not conserved, but momentum is conserved. In both cases, we are not having any external forces. That means the center of mass is going to continue to change with the same rate in both cases, before the collision, after the collision. That's the main idea behind the conservation of momentum, right? So how we answer this question? There was no external force in both cases, in both situations. Therefore, the total momentum was conserved. In both situations, the total momentums before and after were the same. Since total momentum is equal to total mass times center of mass, the velocity of center of mass would be same. As a result, hence, the line would not change. This was the end.